right. Hi, everyone. Welcome to AI and Big Data in Finance Research Forum. Sorry about the technical hiccup. Somehow I wasn't able to come into the panel room. In any case, today we are very glad to have Robert Richmond and Yinan with us. And this is our September installation for the ABFR webinar. And today, I'm trying to lower my head a little bit so that you can see the title. Robert is going to share with us his strong work with Xavier Gebek's, Ralph Koijin, and Moto Yogo about asset embeddings. And Yinan Su is going to be our discussant. We follow the usual format where we have 30 minutes of presentation, followed by 20 minutes of discussions. And then the final 10 minutes will be Q&A. After that, we'll stop the recording and we'll move into a separate chat room for those who want to stay and discuss the paper or related topics even further. So without further ado, I'm going to pass the stage to Robert, and feel free to share your slides. I will monitor the Q&A part to see if there are clarification questions during your presentation. But other than that, we'll try to save most of the more detailed questions towards the end of the talk.
Okay, great. Thanks a lot for hosting me here. I'm looking forward to any comments, and I'm looking forward to Yinan's discussion as well. This is joint work with Xavier Gebek, Ralph Koijin, and Moto Yogo. And as Will said, this is about asset embeddings. So let me jump in here. What do we often try to do in economics? Well, in economics and finance, we're often very interested in trying to find similar firms or similar assets. Now, there's all kinds of different ways that we often do this. You might be looking for firms that have similar levels of risk or similar growth rates or similar expected returns. If you're interested in finding substitute assets, you're trying to find assets that are similar in terms of potentially covariances with certain things. We might look at trying to find similarities in product markets. I can go on and on about different ways that we use similarities in economics and finance. Now, the common practice for how we actually measure similarity of assets is to use observable characteristics. You might go to CRISP or CompuStat and pull some accounting data and see whether a particular firm has a similar level of profitability or a similar market to book ratio as another firm. We have industry definitions. There's all kinds of ways to do that. Now, these characteristics that come off of accounting data are far from imperfect. In particular, standardized accounting data that you would find in typical accounting databases is missing a lot of potentially important things about the characteristics of firms. The example that we like to use here is Netflix. Imagine that you're trying to understand Netflix as a company. What do investors often pay a lot of attention to when they're thinking about Netflix as a company? They really want to look at subscriber counts, right? And that's just not a number that shows up in standard accounting databases, but it's one of the most salient things that investors are looking at when they're thinking about what's happening with Netflix as a company. Similarly, new economic environments call for finding new or creative characteristics. Accounting data updates fairly slowly, and in particular, if you think about events like the recent COVID-19 pandemic or the recent growth of AI or intangibles, we're going to need new ways to think about measuring characteristics of firms that don't show up in the actual accounting data. So this is what this paper is about. This paper is introducing the concept of asset embeddings, which allow us to measure firm similarity. Now, it might seem like just measuring firm similarity is kind of a minor thing, but that's not really the case. These characteristics that we use to measure firm similarity apply to all kinds of different applications throughout economics and finance, and I'll show you some of those here in the paper. Now, before I jump into asset embeddings, let me just start off with an introduction to what embeddings are in the first place. This term embeddings comes from the natural language processing literature, where what they do is they represent words as vectors in some potentially high-dimensional space. So we're, throughout this talk, going to use this variable here, x subscript a. It's going to be some vector in some high-dimensional or k-dimensional space. Now, these embeddings have played a central role in the development of large language models because we need a way to represent words in a way that computers can actually understand them. Now, the classic example that you see when trying to motivate the power of embeddings in the context of large language models is thinking about similarity with words. And in particular, if you have vector representations of words, say the words Paris, France, Spain, and Madrid, you can do math with words on those vectors. You can just take the vector of Paris, subtract off France, add back Spain, and what is the vector that happens to be closest to this left-hand side operation? It's often Madrid. Okay. Now, how do we actually figure out what these embedding vectors are for words? They end up being learned from lots of data, in particular the embedding vectors that they're learning, over at OpenAI, and these things are basically learned on the entirety of the corpus of the internet. And all books and all of these things. So it takes a ton of data. You don't actually pre-select the vectors. You learn what the appropriate representation is of these words. Now, despite the success of embedding techniques in fields like natural language processing, their application in finance and economics is largely unexplored, and that's where this paper comes in. We're going to introduce the concept of asset embeddings. Asset embeddings are just a vector representation for each asset that we're going to learn from data. Now that begs the natural question. What is the right data that we should use to actually learn these asset embeddings? We can draw on a really what we think is a very natural analogy. When you think about trying to learn word embeddings in the natural language processing literature, what do? You look at documents or you look at sentences, and these sentences and these documents organize words into coherent ways. And you use those sentences and documents to actually learn the vector representations of those words. Now, similarly, you've got images that organize pixels in computer vision, and songs organize notes in audio. In the finance context or in the economics context, investors organize assets into portfolios, right? And those portfolios have some similarities with them. And the fact that assets end up in similar portfolios has some meaning to it. So I'm not going to have time here in a 30-minute talk to go into detail, but theoretically in the paper, we actually show a model of how we can recover asset embeddings by effectively inverting the asset demand system. So you can imagine that there's demand for different assets, and that demand is a function of some characteristics that investors use to form their portfolios. We show how we can invert the actual observed portfolios to back into the characteristics that investors are using when they decide to form those portfolios. Okay, so what data are we going to use? We're going to use data on investor holdings. Then the question becomes, which method should we use to actually learn these asset embeddings? We're going to, again, rely on analogies to the machine learning and in particular the natural language processing literature. When learning word embeddings, the traditional approach to do this is something called latent semantic analysis, which is very closely related to principal components analysis. What is latent semantic analysis? The idea is you take a bunch of documents and you look at what words are in those documents, and you just, for each of those documents, you build a vector that counts the number of each word in that document. So then you can build a big matrix of document word co-occurrences. You could run principal components analysis on that to try to reduce the dimensionality. And that's going to give you some representation of the words using the structure of the actual documents, in particular, the word co-occurrence within given documents. This goes back to the late 1980s, I believe, but it's also closely related to the recommender systems that were introduced in the Netflix challenge in the early 2010s. Okay, now, the recent machine learning and AI literature went way beyond these recommender systems and these principal components analysis. The next step after this PCA-based type methods was to build kind of nonlinear or local nonlinear type methods to estimate embeddings. In particular, I'll focus on this word-to-vec based embeddings. Word-to-vec builds local nonlinear based embeddings using a small context of the words that are in a given given a given context of a particular word. I'll go into more detail on that in a bit. And then, of course, we've seen this big revolution in the last, I don't know, what is it, 5 years, with the introduction of transformer models, and in particular, these BERT and more recently, GPT type models that introduce context. In particular, they allow embeddings to have different meanings when they're used in different contexts. Okay, and how are models like this actually estimated? Word effect-based models or BERT type models for embeddings with context, they're estimated using what we refer to as masked language modeling. Okay, and so that's a particular technique, and I'll show you this, that is used to actually estimate the embeddings off of all of this data, that is sentences that you would feed into these models. The question is, how can we apply these methods and the way that these methods are estimated in a finance and economics setting? Okay, let me just mention one more thing before I jump into a little bit more detail here. So even though our focus here is on asset embeddings, we actually, along the way, obtain what we refer to as investor embeddings. These are a byproduct, and these are just learned vector representations of each investor's taste for characteristics. We're starting from data on investors' portfolio holdings. We're going to back into kind of the latent or some set of characteristics that investors are using when they're forming those portfolios. We also end up recovering the tastes or the investor embeddings for those particular characteristics. These investor embeddings have all kinds of useful applications in a finance and economics setting. I'll just highlight a couple of them here, and I'll only show you one later on. They allow us to, for example, classify investors beyond institutional type or size or activeness into more refined measures of what types of investors are. You can potentially use them to identify crowded trades, which is a very important question, both for academics and for industry. And you could use them for performance measurement, extending the characteristics-based performance measurement that was undertaken by Daniel Greenblatt, Tittman, and Wermers. All right, so here's a quick highlight of our contributions, then we can talk about some details. In the paper, we do microfound why using holdings data is a very useful source of how you can estimate asset embeddings. And then we're going to introduce 3 benchmarks that allow us to compare different asset embedding models. This idea of introducing benchmarks largely builds on the success of how the AI literature has evolved. With the introduction of the ImageNet benchmark, which was for the classification of images about, 15, 18 years ago at this stage, you saw just a continuous flow of new benchmarks introduced in the AI and the machine learning literature in order to figure out the power of the methods that are being used for different tasks. We're going to do that in a finance setting here and introduce what we believe are some quite useful and powerful benchmarks in order to figure out how well the particular methods that we are using actually work. We're going to explore different modeling architectures to learn asset embeddings. We're going to build on the language model architecture, but show how to apply this to a setting where you have numerical data, like we have in finance and economics. We'll evaluate our 3 benchmarks for all the asset embeddings methods that we use. We're also going to show how text-based embeddings from OpenAI and Cohere perform relative to our benchmarks, because there's lots of embeddings out there that you can get from companies like that. And we'll also use observed characteristics, standard stuff like FOMA French 5 or 6-factor characteristics in order to see how well our embeddings perform relative to a standard basis of characteristics. I won't have much time to talk about it, but in the paper we talk about how you can actually use earnings calls combined with asset embedding. We can use earnings calls to actually interpret the asset embeddings. This actually extends to any form of text data that you could use, but we think earnings calls are a very useful way to interpret the asset embeddings. That's in the paper. Probably won't have time here. Okay, let me jump into some details here. So I'm going to just show you now a number of the methods that we're going to use to estimate asset embeddings. And the first is going to be building on the PCA-based methods or like latent semantic analysis. In particular, I'm going to refer to this method of recommender systems. There's going to be a recommender system with some parameter vector theta, sorry, with some vector where we estimate some parameters theta of that, which has the asset embeddings, XA, investor embeddings, and then this is an investor fixed effect, and this is an asset fixed effect. So these are high dimensional vectors in some k-dimensional space here. How do we actually end up estimating this vector theta here? We want to minimize this loss function here. So we're going to have some sum over investor I and all of the assets A that they hold. And this is some measure from their portfolio holdings. It could be the log dollar value of their holdings, but we're going to introduce all kinds of different measures there. For now, think about this as the log dollar holdings of investor I in asset A. Okay. And we want to estimate the investor embeddings dot product with the asset embeddings here. We're going to take out investor and asset fixed effects, and we're just going to minimize the mean squared loss on that in order to explain the log dollar holdings, right? So we're just estimating a factor model on explaining holdings of investor I in asset A. So we take all the investor holdings and all the holdings of all the investors, and we can estimate a factor model just like this. These are just regularization terms here. This is K, the number of dimensions of the embeddings, number of investors here. This is just the regularization term. You can introduce that and estimate this zeta here, I guess what it is, using cross-validation. All right, so this is going to allow us to estimate all kinds of different factor models by changing different values here that we introduce for the holdings, okay? So there's a natural question that you can ask. How should we actually measure the holdings of investors when estimating these recommender systems? We're going to look at 5 different implementations of this recommender system in the paper. One option would be to use just a binary value for each stock, for each investor in each stock. 1, 0 for whether that investor holds that stock. And for each investor, we can build that entire vector of binary values for whether they hold that stock or not. And we can estimate this factor model using that value here. An alternative would be to take percentile ranks of the holdings and set the missing values to 0. Okay, that's another one that we can do. And that's just looking at how an investor orders given stocks in their portfolios. And then because we have fixed effects in there, we're effectively just saying if there's a missing value in there, we're going to set it to what is effectively the mean because we have the fixed effects in there. You could say, I want to take log dollar value of holdings, that's this here, and set missing values to 0. Alternatively, you could say that there's actually more information in the missing values rather than just setting them to effectively the mean. You could say, if an investor is not holding that stock, I'm going to set the value of the log dollar value of holdings to their smallest active position, right? So we can introduce more information if an investor doesn't hold that. That's another option. And the last is to only estimate that recommender system on non-missing values, okay? That's the last one that we're going to introduce there. So instead of introducing zeros or filling in zeros, you could just estimate this on the non-missing values in an investor's portfolio. We're going to use a word-to-vec-based model. And the general approach to estimate word-to-vec-based models is to guess the masked word. So how do you do this in the natural language processing literature? You would take a sentence and you say, I've got this, please pass me the blank and pepper. All of us can guess what word goes there, but we need to train vector representations for all of these words. What you do is you mask this word here, salt, and you take some context window, plus or minus a few words, and you maximize the probability of a missing word given the context. So this XC would be the average embedding of all the words in this context around this word salt here. And what you do is you estimate these embeddings in order to maximize the probability that the word here is salt, conditional on the average embedding of all of the words around that. Okay, so that's what you do in the NLP literature. How would we do this with investor holdings data? Well, just like sentences organize words, investors organize assets in their portfolio, right? So we can use that analogy, and we can actually just rank stocks in an investor's portfolio. Say, take the ARKK ETF. We can just sort stocks from position 1 all the way down to the bottom position, and we can mask this stock here, and we can learn the asset embeddings using this mask language task, where we just mask the stock and we estimate the asset embeddings, taking the context around here and trying to predict the value zoom in that setting. Okay, all of the embeddings up to this stage in both our recommender system and in the word-to-vec based model are context invariant, in the sense that for a given asset, say Apple, I just have one embedding for that Apple asset. Now, if you think about this, if you look at an investor's portfolio and you see Apple in that portfolio, the embedding for Apple might have a very different meaning if it's surrounded by a bunch of assets that are tech stocks versus a bunch of large cap stocks, right? Those are very different meanings of the use of Apple in a portfolio, right? In one case, it's the largest stock. In the other case, it happens to be in a tech portfolio. So we also want to be able to potentially care about building embeddings that are not context invariant, but instead have some context to them. That is, we want to adjust the embedding for a particular asset based upon the other assets that it's being held with. To do this, we're going to use attention-based models and transformers. So take HI, I'm just going to go fairly quickly through this, to be the set of stocks in a portfolio of manager I. So take some stock A in the set of stocks that an investor holds. How are we going to update this asset embedding based upon the context that it is held in? Well, how do transformer-based models work? What you do first is you say, for this asset A, I want to get the similarity to all other assets in the portfolio that the investor holds. And to get that similarity, you can just take dot product similarity. Just take the dot product of Apple with all other stocks in the portfolio, and you get some similarity sigma AB, which is the similarity between those two assets. We're going to refer to this XA here as the query and XB here as the key. And then what we want to do is we want to update the embedding for Apple to have some context. In particular, when it's held in the context of investor I's portfolio, we need to update the embedding, right? So we're going to have an embedding for asset A when it's held in the portfolio of investor I. Well, how do you do that? You sum over all of the stocks in that investor's portfolio, and you take that similarity, just normalized here, take the similarity between the assets, and you multiply it by the embedding of all the other assets, right? And so this is how you construct the contextualized embedding. You take the similarity weighted average of all of the other asset embeddings in that investor's portfolio, okay? We refer to XB here as being the value. All right, so how does the attention mechanism actually work in these models? I'm sorry, I'm going quick through this. It's a quick presentation. What you need to do is you need to generalize this. So we use the value XA in 3 places when we construct these contextualized embeddings as a query, a key, and a value. So what you can actually do is you generalize this idea and you project the query, the key, and the value into some other space using some matrices, W, Q, K, and V. And we can compute the contextualized embeddings using this same formula, but based upon the query key and the value being in different spaces. And these matrices, the query key and value matrices, are learned from all kinds of data in order to determine which aspects of the context are important. All right, our full asset BERT model follows typical BERT models. You stack multiple attention layers and you have multiple attention heads. It's got feed-forward layers in between. Sorry, I can't go into too much detail on the structure here. It follows the original BERT paper largely, just adapted to this numerical data by ordering investors' portfolios based upon their rank in those portfolios. All right, so let's jump into the data and the actual estimation of these things. Our holdings data is going to come from FactSet. We're going to focus on hedge funds, mutual funds, ETFs, closed-end funds, and variable annuities. It's quarterly, end of quarter data 2005 through the end of 2022. We have some filters in the data. We're going to compare this with standard accounting characteristics from Jensen, Kelly, and Pedersen. And what are the benchmarks that we're going to be looking at? Here are the 3 benchmarks that we're actually interested in the paper. Our first benchmark is going to be, and I want to highlight something. Our benchmarks are actually all cross-sectional in nature. This allows them to be quite powerful benchmarks in the sense that each quarter there's a new cross-section of data that is introduced. So you can build these new models, and then you can, on that next quarter when new data is introduced, estimate the model on a fully out-of-sample benchmark. Okay, so our first benchmark is predicting relative valuations. This is the log market cap of stock A. What we want to do is we want to first residualize out size. So we'll just run a regression cross-sectionally of the log market cap on the log book equity of these stocks, and we're going to get this valuation residual. This is the thing that we're going to be interested in explaining. So what you'll do is you'll take some set of embeddings, XA, or some set of characteristics, and you're going to run a regression on 80% of the sample where you explain the valuation residual using the embeddings or the characteristics. You're going to fit this gamma 1, and then how do we evaluate the fit of the model? We leave 20% out of sample, and we evaluate the R-squared of this model, of this fit model, on that left out 20%.
Rob, sorry to interrupt. I just want to send a reminder that you have about 5 minutes.
Okay. So
you can plan your time.
Estimating co-movement, we're going to estimate co-movement by explaining the cross-section of returns within the months within a quarter. Similar thing, explain the realized returns using the embeddings, and evaluate the R-squared on the left out 20%. Our third benchmark is masking the second position of investors and trying to predict what the second stock is given the rest of the portfolio. In particular, we want to estimate the probability of the identity of the second largest position in a portfolio using embeddings or characteristics. All right, so here's some results. Benchmark number 1, we want to predict relative valuations. All of these are going to have a placebo in them so that we can make sure that the just randomly generated embeddings don't do anything. Here's beta. Here's the FOMA French 6 characteristics minus size and minus market to book, because we're explaining market to book ratios effectively in this itself. So it's just 4 characteristics. And then on the right here are a bunch of our embeddings models, binary, ranks, filling with zeros, filling with minimums, just on non-missing positions. And then there's the word to vec-based model. The large models are dimensional 10. The red models, base models, are the same dimension as characteristics. You can see that all of our models here for the same dimension outperform the very standard characteristics that we often use to explain valuations. High dimensional models perform significantly better, almost doubling the R-squared when we go to a 10-dimensional model there. You can combine embeddings and characteristics. It turns out there's not a lot of independent information in the characteristics over and above the high dimensional embeddings here. And you can look at text-based embeddings. So you can take text-based embeddings from OpenAI and Cohere, reduce them down to similar dimensions as we saw. And if you look over here, the text-based embeddings perform quite poorly on these tasks, very low R-squareds relative to our holdings-based embeddings. I'll just be quick there. What's going on? Text-based embeddings grab similar firms, but they grab similar firms both based upon both economic and semantic similarity. If you look at the closest text-based embeddings to Apple, it happens to be Appian, probably because Appian starts with APP. Right? Similarly, the closest text-based embedding from OpenAI to Citigroup happens to be some financial firms, but also a lot of firms that just have C in their first name. Right? That's not what we're really trying to capture economically. So these text-based embeddings kind of miss out for that reason, though they do have some economic similarity embedded in them, as you can see there. Here's our explaining co-movement benchmark. This is actually quite a hard task to beat observed characteristics, right? This is the FOMA French 6-factor model, explains about 7% of the cross-section of monthly returns. These characteristics themselves were completely chosen to explain co-movements over 50 years of research, right? So this is a pretty hard thing to actually beat. Our embeddings actually do reasonably well here. What I want to highlight here is if you use our recommender system, filling minimums with levels with or missing values with the minimum, with high dimensional embeddings, you can actually end up beating these observed characteristics. This is about 5%. With high dimensional embeddings, you can get over 7% in terms of explaining co-movement here. Lastly, and on our last benchmark, in terms of explaining the second stock or trying to predict the probability that the second stock is the correct stock, you can see characteristics do reasonably well here. This word-to-vec-based model actually beats characteristics. That's because the word-to-vec-based model is building embeddings that are specifically for this task. Take the local context surrounding a particular portfolio and learn the embeddings based upon that local context and predict that masked stock, right? So it's not necessarily a surprise that the word-to-vec-based model does so well here. Turns out that the asset BERT model, our transformer-based model, does even better than these our recommender system-based models. This model can get up to R-squareds over 50% as you go over to high dimensions in terms of predicting the correct stock in the second position for a bunch of these investors. So this model performs incredibly well on this task. We have stuff on investor similarity in the paper. And we also have stuff on interpreting asset and investor embeddings using text data, which we cover in a later part of the paper that I think is quite interesting and worth looking at, but I'll leave that for you to take a look at. And I can conclude here. So what have we done? Recent advances in AI and machine learning can be applied to finance and economics via asset embeddings. The important insight here is that holdings data is naturally suited to actually learning these embeddings because investors, when they form portfolios, use all kinds of information to form those portfolios. We can invert the asset demand system using all of these methods in modern AI and machine learning in order to back into those characteristics that investors are using when they form their portfolios. We showed how you can actually do that. You need to figure out how to adapt these AI and machine learning literature methods to a finance and economics context. We showed how to do that with very simple models all the way up to state-of-the-art based transformer models. We have a bunch of other stuff in progress, in particular in fixed income, using embeddings to potentially redesign the architecture of fixed income markets. So I will end there, and I am very much looking forward to Yinan's discussion.
Thank you, Ralph. Yinan, you can share your slides.
Thanks for having me to discuss this high-profile paper, asset embeddings, in this, I think, equally high-profile online forum. All right, so I think Robert did a rather good job doing the presentation. Things are pretty clear. I will start with the big picture. I think this paper is really combining two big directions, two big pushes in asset pricing research. One is using quantitative data to complement traditional price, return, characteristic data to think about traditional asset pricing problems. The second one is really bringing this exciting new tools from NLP, from AI, from machine learning to complement finance research, right? So these are the new tools, data, analytical tools, and we're thinking hard about how to combine them for important economics research. And I think this paper is really solving one important economic question. The objective, okay, with these tools, is we're trying to construct asset embeddings. They're just numerical representations of assets, of securities, of stocks. The goal is to use this new kind of numerical representation to go beyond the traditional ones that we use, that we like. Those are the stock firm characteristics. These are very important infrastructure for asset pricing research. We have been using characteristics so long. We use characteristics to sort stocks into portfolios. These portfolios are important test assets to test all kinds of asset pricing models. We also use characteristics to form into factors to explain characteristic-based anomalies. Just looking at the panel today, many of our friends here today have written papers, including myself, using characteristics. So If Robert and co-authors bring this paper and tell us, hey, there is a revamped way, a new way to use quantity data to build a new kind of characteristic, that is so exciting that will bring in much more application to do all kinds of things that we have been doing in cross-sectional and other kinds of asset pricing. So I think this is an important question for its research value. And a lot of the tools we used here are very creative ideas, innovative. The paper is very dense, rich, it's extensive, lots of analysis. So many things to learn from here. Probably I cannot cover all of them. Robert tried to cover, but there's a lot of details in the paper that are also very thought-provoking. So I think that's a very interesting read. So I will just try to review a little bit of the key idea and then talk about some of my comments, right? But before that, I also want to say, when we are using traditional stock characteristics, we have been sort of doing embeddings for a long time already. So stock characteristic is already high dimensional. The dimension is already more than 100 characteristics. When we are using neural network tools, we are already doing some kind of dimension reduction of that 100 characteristics into a low dimensional representation of the firm. We just don't call it embeddings, but it has been existing for a long time. So I've done work that does that. I think just looking at the screen now, Will, and I think Marcus, Sergey, we've all done sort of dimension reduction, shrinking the cross-section of the characteristic. So now with this paper, trying to use quantity data has something unique. Maybe the dimension is even higher. Maybe the data comes in an even more sparse form. So that kind of a dimension reduction requires new tools from NLP research to do this kind of asset embeddings. So what is embedding? Textual embedding, starting from textual embedding, basically you have a model that's trained on large quantity of corpus of textual data. And then every time when we apply the model, you give me a text and I give you a vector that represents the text. So the input text here can be words, phrases, and also can be sentences and even longer paragraphs if now use OpenAI's textual embedding models. So I will talk a little bit in my comments about whether it's word or sentence embeddings. But anyhow, it's a piece of text and it's translated into a vector. The dimension of the vector can be high. I think in BERT it's like 500. In OpenAI's longer form, and it can be 1500. So it's a large dimension vector. So what is embedding basically in this illustration is I give you any text that exists in some other space, but I can map that word into an embedding space. And those words with similar semantic meanings are going to be in a close proximity in this high-dimensional space. For example, wolves, dogs, cat, bananas, and apples. So now I can find similarities between text. All right. So that's semantic similarity. Right. So the key idea of this paper, where is the analogy? How come this NLP tool are going to be useful for our task? So I'm going to use this slide to quickly go through the analogy here. Here's the idea. I'm going to treat portfolio holdings as sentences and create my own new language. I'm going to say, okay, ARK holds these securities. SPY holds these securities. And then I create my own new language. It's a very boring language. It's like calling roll calls, right? Just names one by one. This language has a very simple grammar. It's not a natural language. The only grammar is I need to order the names by their holdings rank. So I'm going to first say the ones that are larger constituents in my portfolio. All right. Then the intuition is if AI is so smart to understand human language, to understand computer language, to even understand music and video, probably AI is also smart enough to understand this special language that I just created. By understand, I don't mean that you have to be truly intelligent or consciousness. I just need the machine to understand in the statistical sense, in the sense that it can predict the next word. It can fill in the blanks if I mask some of the entries. That is exactly what we want. That is so great. If machine can do that, that is really what I want. I want to find assets that are similar to each other according to how investors hold them. I want my machine to be able to fill in the blanks. I want my machine to be able to complete my sentence, so that if my machine can do that, I'm pretty confident that the machine has learned some inherent similarities among all these securities. And then I can use the machine's understanding, which is the embedding, as the numerical representation of all the firms. I think that's the gist of the idea in a nutshell, right? So I create my own language and let the machine to learn this language. And if the machine can predict my language, then the machine can give me some numerical representation that I can use. All right, so let's just train an NLP model on all these language that I can collect. So that is a language corpus that I generate from my holdings data, right? And then I look at the neuron activations, that will be my embeddings. Yes, I think that's a creative idea. Underlying idea, there's actually theoretical analysis in the paper that's holding reflects asset characteristics. So similar firms should often appear together. Different investors that might have different styles. One investor is size, the other is momentum. Then I can track different aspects of the firm according to which of the styles of the investors hold those firms. So that's the rough idea behind this method. So my comments from now on are going to be a little bit more technical. I'm going to think harder about the methodological connection between these NLP methods and our demand from a finance research perspective of what kind of characteristic we want to build. So my idea is the transfer from the technology to finance research is not necessarily always straightforward and requires some careful consideration. So to begin with, I want to, I think Robert did this, but I want to clarify again a little bit different concepts of embedding, especially in this transformer model. One is input embedding. That is for each token, I have a numerical representation, but that is used as input to 12 layers of a transformer neural network. The output of that is so-called the contextualized embedding. So the contextualized embedding gives you the semantic meaning of that word within that sentence in relation to other words around that. That's very important because BERT originally, I think the main function is to do translation. And if you want to think about translation, context is very important. Otherwise, I can just look at a Chinese sentence and use a dictionary to translate every word to English. And then if you piece together all those English words, that's not English because you have to consider context of each word's meaning. So the contextualized embedding is the output of the transformer model. So maybe we can look at that as in a sequential way. I have word number 1, 2, 3 to n, and input embeddings are here. The outputs are contextualized embedding. And there's once more the sentence embedding. So I can use the embedding of a special token, like a placeholder token in this sentence. So that token's embedding will give me the whole meaning of the whole sentence. All those words. It's not any single word. So this is sentence embedding. All right. So let's bring this analogy to our application, right? We have input, contextualized embedding, and sentence embedding. Which ones we are using, right? And what do we want? So I think by the end of the day, we want characteristics that are indexed by firm, comma, time, or firm month, or firm quarter, because traditionally we have size, value, momentum. It's each firm, each month. We want this kind of a data structure, firm, comma, time. All right. And then what embedding gives me is if I do contextualized embedding, think about our sentence. Our sentence is one investor. One word is one firm. So the contextualized embedding gives me an embedding in the level of a comma investor. So I'm contextualizing in investor. I'm not contextualizing in time, right? But then in the results section, it seems that the paper reads like, oh, we are using input embedding, but we could also use contextualized embedding, but we're not really using that. So it's a little bit not clear, but I think they eventually use the input embedding, which is only indexed by firm, by word. So it's only indexed by A. So it's again not contextualized in time. So there are some problems that might limit the application of this. Number one is, like I said, there's no time if I use this input embedding to characterize a firm. So if I train the whole sample period in one model, Then throughout the period, whenever I give you a name, Apple, the vector that output from the model will be static, never changes, right? Or if I do this cross-section by cross-section, well, it changes, but it's kind of isolated. I don't have a time series of the firm's size. I don't have a time series of the firm's value. So I'm a little bit confused here. So for example, I can ask this question. Can we still do the simple tasks like characteristic sorted portfolio if I only use input type of embeddings, right? And the question number 2 is, I think for BERT, the most important part of the technology is contextualized embedding and the sentence level embedding. It's not input embedding. It's called input embedding, so it's not the most key output of BERT, right? So sentence embedding is. So if I only use input embedding, it sort of feel like an overkill because most of the parameters happen after input embedding, right? There are 12 layers of big networks here, but I only use input embeddings here, right? So if I only use input embedding, I could probably go back to Word2Vec, those older technologies, right? So I think about this problem. I want to make a proposal. I know there are engineering details to figure out, but I want to make this proposal that overcome some of the problems here. So my proposal is to think about so it's basically like a transpose of the data. I want to think about each firm quarter as a sentence because I want my embedding in the level of firm quarter. And then I do sentence embedding of this sentence. So here is my data structure. Is Apple in this month is held by these investors. Microsoft this month is held by these investors. So now I want to characterize firms by who holds them, right? So then I embedded all these sentences. I learned sentences in this structure. It's firm month, and the constituents are who holds them, right? It's different from before. Before it's like each asset is each investor holds what securities. This is a transpose. Now I do each security is held by whom, and then I got a sentence level embedding, right? I use sentence level embedding. That's the contextualized in sentence. If I do this, the output is in the right data structures. I get the firm time panel structure back, right? So now I have Apple in this month, I have a vector. I have a Microsoft this month, I have a vector. I think this is, at least it's come to my more familiar data structure. The panel structure is back. And then I can also do out of sample analysis. I can do out of sample characteristic in time. So I can train a BERT model in sample. I cut, okay, before 2020, I train. And then I hold that model. And then for newer data, I have newer sentences. I give you a sentence, you can get a characteristic out. So then I have out of sample characteristic that is available in time. It's live data, right? So the underlying assumption is the investor properties are stable. I'm learning what kind of a security you are according to who holds you, right? So Robert mentioned the investor BERT model, and that kind of does this transposed input, but they think this is they view this as a way to embed investors. My proposal here emphasizes on sentence level embeddings. I'm still embedding firm, but I'm embedding firm, comma, quarter. And also additionally, additional comment is I think it's possible, it's at least worth trying to encode numerical information into that, because in finance research, we have a lot of structured data. So maybe the sentence can be a structured, like a name, and then I have a field that gives you a number, it's a holding, it's flow, maybe more information can be learned by the network in this fashion. So this can be more valuable for application in finance problems, right? So that's most of my comments, and I want to, in the end, take a step back into the big picture. I think these are, once again, using quantitative data and AI machine learning tools. These are very valuable tools. There are all kinds of combinations of how we apply the tools for different important economics research problems. The organizer asked me to talk about the perspectives on some of the related questions. I just want to say this is a very exciting field to apply these new tools, to think hard about finance problems that we already thinking hard about. So I'm doing some work that in this area using quantity data and machine learning. I'm going to give a few examples. Number one is called trading volume alpha. So this one is looking at volume data. So that's a complement to traditionally looking at price and return data. We have been using neural networks to predict the returns, but now this time we use neural networks to predict volume, and we transfer that volume predictability into economic value in the context of after-cost portfolio optimization. And we find huge economic value in terms of portfolio performance. We call that trading volume alpha. So technology we use are neural networks and transfer learning. Another paper, very recent paper of mine called Quantity, Risk, and Return. We're using quantity data, flow-induced factor quantity to complement a traditional factor pricing framework. We find that not only we need risk to explain expected return, but now we have a BTQ model called beta times quantity. So factor exposure and quantity together explain the cross-section of expected return much better. We can use this to predict the return. We can use this to to tame the factor zoo problem. And then last one, I have ongoing work that is thinking about embeddings, but this is still in the embedding of text. And I'm trying to use that to tame the narrative zoo. There's all kinds of textual data that we can use to build a narrative, the economic time series, to track important economic concepts. For example, we have one that tracks recession. We have ones that tracks economic policy uncertainty. But now this time we build this web-based service that allows economic researcher to track any interested narratives based on a textual query. So the backend, we use all kinds of OpenAI's textual embedding and generative AI methods. And towards the end of my discussion, I want to just quickly show a demonstration video to show our web-based service that we will put live soon. So basically, a researcher just input one query, can be any topic that you're interested in, hit enter, and I can track the importance of this economic narrative in all kinds of corpus, say the Wall Street Journal news corpus or firms' earnings announcement or conference call corpus. And then this, again, there's a building an important infrastructure for all kinds of economic and finance research. All right, so with that, I'd like to conclude my discussion and look forward to talking with all of you online or in person in the future. Thank you.
All right, thank you very much, Yinan, for the great discussion. Rob, you have a opportunity to respond, but we also want to mention to our audience that you can write your questions in the Q&A. We also replay the webinar on YouTube and other platforms where you can watch and rewatch the discussion. Okay, so I don't know, Rob, if you want to quickly respond, or
yeah,
I also have multiple questions I'm happy to ask as well.
Yeah, I'll be brief so that we can get to questions. But thank you for a great discussion. A couple of points. Yes, your point is very well taken on using the sentence, like the CLS token or the sentence level embeddings to extract the contextualized embeddings. I think that's actually, in a large way, a cleaner way to build the asset and the investor embeddings. So we are indeed working on a version that uses those. We kind of, yeah, we're actively working on that. So thank you for bringing that point up. It's the right way to use the BERT model, I think. We are using the input embeddings. We are using the contextualized embeddings in the stock prediction exercise, right? So for the predicting the second stock, when we use the BERT model, we just feed it the entire portfolio with the mask position and predict the second stock. But for all other tasks, we're using the input embeddings for the BERT model. But your point is, I think, exactly the right thing about the sentence level embedding. One other thing on the timing. Everything that's written down is basically for a single cross section at a single point in time. But we do that period by period in order to obtain embeddings that are time indexed. Because we have separate cross sections of holdings at each point in time. So we do have a time series of embeddings, but there is still a subtlety in terms of being able to do portfolio sorts with these embeddings because they're each estimated with a different cross section at each point t. So I think your point on the sentence transformers is also useful there.
Yeah. I'm glad that you find this somewhat helpful, and look forward to if you have new development of this exciting research. Yeah.
And we have a question from Mayan.
Great presentation, Rob, and great discussion. So I actually have like about 1 million questions, but I'm gonna try to keep it short. So the first question was, I mean, basically related to time, and you partially responded to it, that it is you're doing cross-section by cross-section, okay? But you're like usually in these like ML models, the underlying assumption for training set is that it's stationary. While in the I mean, if you want to use the whole like time series to train one model, then we break the assumption of stationarity. And also stuff like, I don't know, like regulation change. It might not like Apple. I mean, there are, because by nature, the nature of these asset holders, the nature of institutions are different. They can or they cannot hold things together. So that is another thing that can be added to your context, okay? But more importantly, I was like also thinking about this time, especially because like if you want to go to in terms of the features, okay, if you want to go very high, okay, then the data in one cross section might not be, I mean, depending on how large you want your feature vector to become, you might run into these notions of like, okay, the data is not enough for training. And that goes to my last question, which was basically, are the performance numbers that you showed are in sample or out of sample? So basically you are training with.
Yeah, so let me go from the back on those. So each of those performance numbers are out of sample with the 20% left out sample. They're averaged over the entire time series. So within each quarter we do that. We cut it 80%, 20%, and we estimate on the left out of sample 20% within a single cross section. Those R-squareds are averaged across all of the time series that we have there. Now, backing up to your point on introducing the time series, we have explored a bit in terms of doing something like a pre-training of the BERT model on a long sample and then just updating with additional time series. We're in a bit of a state right now where we actually have enough computing power and enough data within a single cross section to estimate what we want to. And so that really allows us to estimate a separate set of, say, contextualized embeddings in every single quarter if we want to. Now, you're on the boundary of how much compute you have there, but we have a different setting here with finance, and particularly with holdings data, that does allow us to take each cross section at each point in time. And we know that that is unique. The LLM stuff, you don't have timestamps in these sorts of things usually. So it's a bit of a different exercise. So we're able to kind of exploit the nature of the fact that we have a very large cross section at each point in time. We have explored some of these things. We didn't find a huge boost in terms of the performance of the asset BERT model in particular, but by training kind of and then adding in additional quarters. At least that's for this particular model. It doesn't mean that it's a generic.
Thanks, Rob. And we'll get to Marcus' question in a bit, but there's a question from the audience just asking, if the investor number is larger than the dimension of the embedding, how to do that, but I guess the embedding is dimension reduction, so that's fine if the investor.
Yeah, maybe I can just give a little bit of sense of scale. So for a given cross section, take a given end of quarter, most recent 2022 Q2, we'll have about 3,000 stocks in there and about 9,000 investors. And we'll reduce that dimension to say 128 dimensional investor embedding on the highest end, but substantially smaller than that.
Right.
We have plenty of data to estimate that.
Yeah, and also just related to Mayam's earlier question, I think maybe you can also describe that how large language models or these AI models, sequence models, they don't fully get rid of stationarity assumption, but they do it better than traditional time series models that we have in any case. And also on the embedding part that Yinan was saying earlier, it's true that many papers use asset characteristics, but they typically don't create a asset-specific representation in that abstract space after passing through the neural nets. So that's something your paper does uniquely. So that might be one way to argue about that. And then just in terms of the cross-section versus time sequence, I guess what's key is not really the input versus the contextual. As long as they are all sequence models, what's key is the separation between cross-section and time series, right? So there's still information in the cross-section. In that sense, what you are doing is still helping with the model. It's just that in the time series, when you do the sentence level embedding, with taking the firm quarter or firm month, that's going to probably get you additional information, which might be useful. I want to get to Marcus' question as well. Yes.
Maybe in the interest of time, I can ask it in our informal part, and we can conclude the official part of the webinar.
Okay. So let's give a round of applause to Rob and Yinan for their presentations and discussions. I don't know if we do the virtual applause. And I do want to mention we have several fantastic talks coming up for the rest of the semester and also in the spring. So definitely follow our website. We'll be posting that soon. And Dimitri Livden is going to talk about economic impact of payment system stress. And Nancy Wallace is going to present work related to using machine learning to measure, flood risk in California. And there are many other upcoming webinars that are very exciting. So with that, I'm going to conclude today's webinar, at least for the official part. Now we can all move to a unrecorded separate Zoom room to chat more and ask the more critical questions. Happy to see you all, and thanks for joining us.